Afternoon, everyone. Welcome to the 2020 Georgia Tech Manufacturing Institute GTMI Fall Lunch and Learn Lecture Series. I'm Paige Shee, Strategic Partners Officer for GTMI. The GTMI is one of 11 Georgia Tech interdisciplinary research institutes that uniquely focuses on manufacturing research, development, and deployment. We help tackle the grand challenges of today's manufacturers and assist our partners in moving innovations from the lab to the market. GTMI has a wide array of facilities and equipment located on main campus for basic research and nearby on 14th Street for applied research in the Applied Manufacturing Pilot Facility, also known as AMPF. GTMI's mission includes education and workforce training, collaborative partnerships with industry, academia, and government, as well as thought leadership. Each semester, GTMI hosts a Lunch and Learn series. This fall, our sessions are held every Monday at noon as live online events. These sessions are excellent opportunities for Georgia Tech faculty and students and researchers, as well as a growing global manufacturing community to learn and share advanced manufacturing knowledge. To ensure a smooth presentation experience, all audience members are automatically muted at this time. If you have questions or comments for the speaker, which we encourage, please feel free to use the Q&A panel on your screen to submit those as they come to mind throughout the presentation, and we'll address those at the end with the speaker. Today I'm very pleased to introduce Chuck Zhang. He will present current research and future plan for composite joining and repair technologies. Dr. Chuck Zhang is the Harold E. Smeller Professor in the School of Industrial and Systems Engineering at Georgia Tech. He's also an affiliated faculty member with GTMI. He received his Ph.D. degree in industrial engineering from the University of Iowa. Dr. Zhang's current research interests include manufacturing cybersecurity, additive manufacturing, composite structures manufacturing and maintenance, and biomanufacturing. His research projects have been sponsored by major federal agencies including DoD, NIST, NSF, and VA, as well as industrial companies such as ATK, Cummins, Delta Airlines, and Lockheed Martin. Dr. Zhang is a fellow of the Institute of Industrial and Systems Engineers. He currently serves as the principal manufacturing technologist for the newly established Secure America Institute, which focuses on technology development and deployment for cybersecurity of manufacturing supply chains. Dr. Zhang has published over 200 journal articles and 220 conference papers. He also holds 25 U.S. patents. Thank you very much for joining us, Chuck, and thank you to our audience for joining us today. You may now begin your presentation.
Okay, thank you, Paige, and for the introduction, and also thank you all for the all the attendees to take the time. This is probably your lunchtime to come to this webinar. Today, I'm going to spend maybe about 40-45 minutes to present our current and research and the future plan for the composite joining and repair technology areas at GTMI. So if you look at this slide, basically this is what we're going to cover today in the presentation. I will basically introduce the significance and impact of this area for work in the composite joining and repair. We call it CJAR in short. And also I will spend a few minutes talk about a project that we got from NIST, which kind of started this area of research and road mapping activities. And then I will spend some time to present our ongoing and planned research in this area. And finally, I wanted to conclude this presentation by introducing a new project that we proposed to National Science Foundation to establish a IUCRC. It's called an Industry University Cooperative Research Center in this technology area. Here, this slide, I think you probably will see this. This is the timeline of the composite joining and repair work. If you look at the why this technology area kind of get more attention recently in the last 10 years or so, is because there's a significant increase in composite usage in transportation industry. For instance, Boeing 787 and Airbus A350 both of them boost the use of composites in the aircraft manufacturing, because both of these aircraft use more than 50% composites in their structures. And also, if you look at the automobile industry, it's also started less than 10 years ago. There are several car makers start to produce composites vehicles, or you can say quote unquote composites, because they use not 100%, but a majority of the structures are made by composite. For instance, the BMW i3, it's a lot of the materials in this car is made out of carbon fiber composites. Most recently, if you look at the bottom right, there are two vehicles. They're actually pickups. One is Honda, the other one is GM, and they actually make the major structures like the truck bed, the box at the on the back. It's using the carbon fiber composites, and so they both actually won some awards. Actually, this is a recent, like 2017, 2019. On the upper right, actually, is another area that very important. It's to our national, security, and because the a lot of the military aircraft, both fixed wing and the helicopters, and they actually many of them are very old legacy aircraft, but there are a whole bunch of them, and there are thousands of them, and still flying. And some of the age is over 50, 60 years, and then so they need a lot of work to be done to maintain them. And so all of this require development in CJAR, composite joint and repair. And this actually slide shows the financial impact or economic impact of this area of work. I don't know if any of you have some knowledge about this. Actually, look at the aircraft. When you purchase aircraft, they depending on the model, right? So it costs maybe over 200 million to buy one. But the maintenance, we call it MRO, okay, maintenance, repair, and overhaul, okay, maintenance costs, it can be very high. For instance, for primary aircraft and structures, and it costs about 7.7% of the purchase price to maintain the main structure of the aircraft. So for example, for Boeing 787, the purchase price is $218 million, but in the life cycle of the aircraft, down the road, let's say 20 years, the airline company has to spend $16 million on the aircraft frame MROs. So that's a lot of money. And so just give you a number, if you look at the last bullet, if you look at the all the A350 and Boeing 787 aircraft that delivered by next year, the total airframe lifecycle maintenance cost is estimated at 34.1 billion. So that's over 34 billion just for the airframe maintenance down the road. And also on the right side, there's just a specific example of, and this is just a composite, skin of the engine of an aircraft, and you can see that the repair cost actually is about 1/3 of the replacement cost, like if you buy a new one. So it's very expensive, and also grounding a Airbus A350 can cost the airlines over $1 million per day. Actually, it's because the delayed flights or cancellation flights, all that costs a lot of money. So you can see there's a big financial and economic impact of this area of work. Of course, like I mentioned, the national security and societal impact, this is in addition to the economic impact. You can see that definitely, right, the composite joinery repair work can help improve the military equipment readiness, but also reduce the cost for maintenance for the national security, applications. Societal, I think everybody probably has a lot of experience on this when you fly. You definitely want to have a good equipment for the aircraft, right, so that it's safe, but also you want to, on time, right, on time rate high and no cancellation, no delays. And again, the emission reduction, if you have lighter aircraft and then you save energy, that will help societal the impact. And the other thing I want to quickly mention, there's a number there is I don't know if you know that 60% of the flight delay is related to aircraft maintenance, not by weather. Actually, when you fly, if airline has cancellation or delay, they always say, oh, it's due to weather. But actually 60% of the time is because of the maintenance. So now we know that it's very important, and there's a lot of need and demand for this area for technology development. And also they have a lot of impact financially, and also the national security, societal impact. So in 2014, so about 5.5 years ago, I would say, that Dr. Ben Wan, who's the executive director of the GTMI, and myself, we wrote a proposal to NIST, the National Institute of Standards and Technology. They have a program at that time called AMTech, Advanced Manufacturing Technology. That program provides funding for a team of like a university or industries to develop technology roadmaps instead of technologies, but they want to develop like what is the future development trend in a specific technology area. So we wrote the proposal and we received that grant. And then when we start the project, what we did is we actually polled the industry members. Many of them actually, we went to the CAIAC conference. In that conference, we polled, we had actually special session, we polled 80 companies. And then from all this feedback from industry, we actually asked them to rank what are the technologies in composites that they want us to develop a technology roadmap. And after we, analyzed the polls, the feedback, it's a little bit surprising to us that this top 3 areas came up are composite joinery repair and integrated computational design tools and database, and the scalability of composites. So we thought there are other, fancy, like nano materials or, structural health monitoring, all those actually they were lower. So we thought that, okay, maybe industry want us to study this composite joinery repair. And of course, the other 2 are related to this. So we basically combine them. We start to work on the roadmap. And this is a US map that's showing that we involved over 50 industry companies and government agencies spanning the whole composite supply chain, including the small to medium sized enterprises, SMEs. And so this is basically the members or industry members and government agencies that we involved during this technology roadmap development. And this project is called CAIAC, CAIAC, CAIIAC. And this, during the CAIAC projects, so we basically create this consortium. And we use this consortium to develop the roadmap. And the goal at that time we set was with this industry feedbacks or input. They all recognize that current composite joinery repair work is done primarily manually with experience-based processes. So inspection, repair, and then the quantification, or all this are done by primarily manual processes, and so they're not very reliable. Many times they're not repeatable. So the goal is, after this 10 years, 15 years development, we want to set the future, right? The goal for future is automated, right? Rapid and science-based reliable repair. We call it AR3, automated, rapid, and reliable repair. How do we get there? That's the roadmap, technology roadmap, work. So we wanted to know what are the current technology, state of art, and what is the issues, what's the gaps, and then what is the future technology development, the trend, and then analysis of those trends. So we actually adopt the this technology roadmap development methodology, and we basically have this we call it the two phases. Phase one is to develop this roadmap. The phase two is to have this consortium to implement by conducting projects and forming more technology development and demonstration, especially like facilities and the test beds. So in the first phase, that's the NIST project. So basically, we gather the data from the industry experts, and then we look at not only the input from these experts, but also we look at the scientific publications, patents, and databases, and then combine those data and formulate it into a kind of roadmap. And in the roadmap, we not only look at the technologies, but also look at their maturity, like TRL, MRIL levels, during this 10 to 15 years development. And then we validate the roadmaps by those experts. So that is phase one. I'm going to talk about, this phase one work. So in fact, the first thing we did, I believe it's 2015, and then we look at the current roadmaps available that are developed in the last about 15 years in the area of composites, and we found many of them, actually over 40 those roadmaps are available. So we thought, well, we need to do something different because they already have 40 roadmaps. Why do we do another one, right? So we thought that our meta roadmapping, which I mentioned earlier, like we combine the scientific, publication data in addition to the experts, right, from industry, but also the patents and all that. So that is one uniqueness of this road mapping effort. The second one is we involve or include the technology maturation parameters, like in this case, TRL, MRL. We also created another readiness level. One is a business case, and the other one's ecosystem. So we want to look at if this technology, not only technology-wise it's mature, maybe manufacturing technology is also mature, but what about the business case and ecosystem? We also look at that during this technology road mapping effort. And finally, I mentioned earlier, but we actually we want to have a full value chain engagement, meaning that we involve not only those large corporates, but also the small to medium-sized enterprises in this field into this road mapping effort. So this, I mentioned this earlier, but this is a little more details how we did this meta road mapping. So we combine this data from publications, right, and patents, and then of course, we got the data from industry experts through several routes. One is we hosted several the on-site workshops. Some of them were in Atlanta, Georgia, here in Georgia Tech, but some others were in conferences held elsewhere. And we actually, through those workshops, we collect a lot of data. In addition to that workshops, we also did a lot of phone interviews to a specific, experts in a specific areas. So we actually made many calls. And then we combine all the data. That's phase 4 that we call a triangulation. So basically, you get all those data from these 3 sources, and then we combine them, make this technology roadmap. These are just a sample of companies and government agencies we involved during this technology road mapping effort. So you can see there are OEMs like Airbus, Boeing, Lockheed, and all those companies involved in this road mapping effort. And then we have users or operator like Delta, Sikorsky, and then material suppliers. Anko, Salvi, they have experts and engineers involved all the time in our efforts. And then, of course, the equipment vendors, R&D organizations, and training providers. Like Abertis is actually big in composite training, so we actually involve them. And then there's some, the community colleges and local, technical colleges are involved in our efforts too. We also, if you look at this technology roadmap, right? So first, we actually look at what technology areas we wanted to work on. So this actually shows that at that time when we developed the roadmap, we split the whole CJAR technology into 6 areas: materials, processes, design tools, database and standardization, right? And then NDE inspection, equipment automation. The last but not the least is workforce training. So we actually look at all the 6 areas. What is the current state of art? What is the industry need? What are the gaps, right? And what are the future technology development that can help in that area? So we actually did for each of these areas, we did one roadmap. And usually each roadmap consists of several charts. I'll show you that later. So I want to quickly mention about how we did this scientific publication analysis, right? And then the patterns analysis. So actually we, basically this is like a data mining work. So basically we look at the ISYE publication database, and then we look at how many publications in specific technology area. Like in this chart shows the NDI. So basically we look at how many publications in each year from very early, like 1960, all the way to 2015. And then in this 55 years, and how many publications in this NDI area. So you can see, especially in the last 10 years, this area's got a lot of attention. And then, more importantly, we can do some quantitative NDI analysis. In this case, this is not just regular NDI. We call it quantitative NDI, means you can use NDI technology to quantitatively analyze what is the defects in the composites and what is, let's say, strengths, residual strengths in the composite. So you can see this areas. You can see that in the NDI, there are totally publications. That's the blue lines. But then we also look at what about those publications in specific application areas like aerospace, auto, and then that's the other lines are showing. And then there's also patents, like the orange lines, the patents, and you see basically their trends in the last 55 years. We also find out, actually we did some analysis of major technologies like battery technologies, material, thermoplastic material technologies, all those. We look at usually how long it'll take to have a specific technology to mature from a patent that first filed to the mass application in industry. And we actually did some statistical analysis in here, and we found that most of the engineering technology, it took about 25 to 30 years to mature. So actually based on that, we look at the quantitative NDI, the first patent in this engineering, like aerospace, auto manufacturing applications. It was filed in 1994. So using our, this kind of like timeline analysis, you can expect about between 2020 and 2025, those technologies should be matured to commercial, application, which means maybe like, within the next 5 years, probably there will be more machines available in this area, more mature technology that can be mass, applied in this industry. So that is kind of a we did some kind of a pretty interesting data analytics, big data, analysis from the publications, and then we found out that there are a lot of useful information that we can build into the roadmap. And then this is additional some data analysis work we did, like for citation. Actually, you can look at the publications in certain area. What about their citation burst? That means in which time frame that this area of work or this publication in this area that received the most citation. And then you can see this is also related to NDI, NDT, or NDE. There are many keywords we put in there, like for instance, ultrasonic testing, acoustic testing, X-ray inspection, all those. So you can see this shows the trend, like what are the technology in the early years, 1980s, and up to like about 2015, that you see a lot of technology that they moved. Some developed many years ago, and then they have in certain time frame, like 5-10 years, were pretty popular or hot, but then they kind of disappeared. And some of them actually came back again, like the acoustic or ultrasonic things. It was hot in 1980s and 90s, but it disappeared for a while. But then now it's coming back again, probably because of the progress or advancement in that area, or computing technologies can help that. So this actually will also help us to develop the roadmaps. This is about the readiness. So for each technology area, when we develop a roadmap, we also look at what is this TRL level of this technology at current stage, and what is 5 years down the road, 10 years, and 15 years. What do we expect them to grow? And this also, a lot of this data is from publication, but also from the industry experts, the input. And so finally, about 3 years ago, we finished the project and we published this technology roadmap, like I mentioned, in the 6 areas. And then we even made a book. And so of course we have electronic version. If you're interested in that, please feel free to contact me, and then we'll send you the electronic version of that. So this is just give you an example. This is one of the example for just one NDI areas. So this one is the general NDI. So you can see it covers several technologies areas. And for instance, like a very old technology, like a visual inspection, all the way to the ultrasonics, and there's several ultrasonics, right, and radiologies, and then terahertz imaging, so all those technologies. And then on the right side, it shows the 15 years time frame, how we expect those technologies to develop or to mature. So for instance, if you look at the lamp wave, I'll just pick an example, like lamp wave. The That's one specialized ultrasonic technologies. So we thought that it'll take about 10 years to develop. And the color code, if you look at the, there's a bar, right? On top of the bar, there's the current technology, levels, and then there's futures. And then there are 4, bars, and each bar represents different things. Like on the left bottom, it shows the legend of the bars. So the first on the left, it shows the performance, and then safety in the second, and then affordability, and then the efficiency. So if you see a bar number, the bar, the color, the green, that means that area is good, is high, okay, like performance is good. But if you look at a bar that's red, that means it's not good. Like for instance, the nonlinear ultrasonic, right? So the first bar and then the last bar were red. The first bar means performance, right? So that means the accuracy or the is still kind of not very good. So it's right now, and in the future, of course, after 15 years, it'll turn to green. And also the cost, right? It's a little bit high now, but in the future, it's better. So this shows not only the technology growth, but also we actually rank them in terms of those 4 things. Below the bar is the TRL level, MRL level, and business case level number. Like T2, that means TRL level right now is 2. After 5 years, it's 9. Whatever. And then so that means in the next 5 years, this technology will probably receive a lot of development. So this actually just show one chart. Well, we have many of them, like materials. We have materials that have multiple charts, and then the equipment, automation, they also have a chart. Okay, so that is kind of showing the roadmaps. So this is a major work we did, and then after that roadmap developed, we actually, with the industry experts' help, we said, well, let's look at the vision of this technology development in the next 10, 15 years, right? So what are the, after, let's say, 10, 15 years, we said, well, we want to achieve this automated, the efficient, reliable repair process. What are the key technology areas that we should develop? And those actually listed, this slide listed 6 major, technology areas that we should develop and mature. And we call it digital composite joining repair. So a lot of this rely on digital technologies. So for instance, the first one, we want to have a structural damage evaluation before the repair. Right now, most of this work, like I mentioned, is done by manual process. So you'll see a technician goes to around the aircraft. They actually use a coin to knock the structure, and they use the airs to listen. And that's a lot of companies are doing right now. So they're basically experience-based, try and error kind of a process. But in the future, we would like to have the digital AR or NDI technologies so that the technician can remotely, monitor this, damage evaluation process. And then the composite joining repair analysis planning using computational models and tools and databases. So this is also missing right now. And then material preparation, inspection using the digital processes, and then robotic automated, scarfing, joining process, quantitative NDI. So after you repair it, how do you know it's done properly? There's a big need in this area. Quantitative and reliable NDI techniques. And finally, we have seen this trend because of the IoT, all the digital technologies. A lot of sensors are built in the aircraft structures and also being used in the repair process. How do we make sure that we can develop effective data analytics techniques, and also we do it securely? So the cybersecurity is a big issue in here. You don't want to have a sensor on board the aircraft that are hacked by hackers, and then it generates the wrong information, right? So this all are very important areas to work on. And then this consortium also helped us at the end of the project about 2 years ago. They actually helped us to develop a laundry list of projects, okay, for large-scale, long-term projects, but also medium-scale, short to medium-term projects. So actually, we are using that as a guidance to develop our, the research programs in GTMI. So I'm not going through this, but you're going to have this information later, so you can look at this list. So next, I want to kind of show you the GTMI capabilities and research in this field. I would say GTMI has capabilities and competency in these 4 areas. One is that we have, in the last 5-6 years of work, we have built up a lot of fundamental understanding of materials and processes in composite joinery repair. We also have a comprehensive set of equipment for this area of work. And also we have a lot of collaboration with other schools, ISYE, ME, MSE, and others related units. And we have built a very strong capability in data analytics and cybersecurity for composite joinery repair. Finally, we have very unique work in the area of NDE, especially quantitative NDE, for they call it kissing bond detection. So, which is a very major problem for aerospace applications of composite, bonded structures. So I'm gonna show you some detail of our work in this area. So before I go to the projects, I want to quickly show you, this is what I mentioned, that we have been building our capabilities in composite joinery repair. So I call it a digital composite joinery repair lab in GTMI. So right now this lab sits in the GTMI building, Callaway Manufacturing Research Center. And we are also expanding it so that we probably will have a bigger space in AMPF, which is located in 14th Street. So this actually, this lab right now hosts a lot of equipment that are in the testing facilities that are for the composite joinery repair. And so here I want to quickly show you 4 areas of our work in GTMI that are related to composite joinery repair. One is monitoring and bonding, monitoring of the bonding process with advanced sensing, and the other one is quantitative NDI, and then the computational modeling and AI tools for the composite joinery applications. So finally is a plan of work that we're thinking about to use augmented reality for CJAR operations. So here is a few years ago, we start this area of research. We find out actually a lot of the industry that companies, they do the composite joinery repair, but then they, like I mentioned, they primarily rely on the manual processes. They don't monitor the bonding process very well because there's no technology. So what we thought is, well, there are a lot of new development in sensing and manufacturing, advanced manufacturing, like 3D printing. So we want to explore to develop some kind of advanced sensing for composite joining specifically. So this actually idea came out is, if you put some electrode on the surface of, let's say the adhesive, right? Adhesive, yeah. Maybe I should introduce this a little bit. When you repair, let's say, aircraft structure, okay, what you do is you have, let's say, a piece of material on top, a piece of composites. Both are composites on bottom, and then you put the adhesive film. Usually, it's like pretty thin, like a 1 millimeter, 2 millimeter thick adhesive film in the middle, and then you pack them and vacuum bag them, and then you put it in the either oven or autoclave, or it can be like heating blanket. So you heat it, so the adhesive will melt and it will bond this two pieces of structures. And if you can put an electrode on one side of the composite, and then the other set of electrode on the other piece of the composite, if you arrange them in a certain pattern, it can be used as a sensor. So what we did is that we have a very in GTMI we have a lot of advanced manufacturing capabilities. In this case, we use printing electronics to print those electrode, miniature electrode, as a micron sized electrode, and then we basically can put that between those two pieces of bond structures, and then we can monitor the the pressure during this bonding process, but also the curing of the film during this bonding process. So this actually is a part of the Delta supported projects on monitoring this composite aircraft repair and maintenance, and the result actually is pretty good, and we validated with our testing equipment in the lab. And the other work that we're doing is that if you probably know this, if you have something at home that are broken, you want to glue them together, you buy a super glue right from, say, Home Depot, and then you probably wanted to clean the surface first a little bit, right, make it rough, and then you put the super glue, and then you bond them. Similarly, in the composite aircraft repairs, same process. You want to clean the surface first, and then you put the adhesive film in the middle, and then you bond them, right? So how do you clean them? How do you make sure the surface is clean, and it's also the surface is well suited for bonding with that adhesive? There's a lot of scientific work need to be done. So in this case, we actually use for cleaning, right? Certainly you can use like sandpaper to clean. That's where a lot of industry partners are doing. But actually, you think about if you use sandpaper by a technician, it's not reliable because people are different, right? And then in the morning, even same person in the morning, you ask him or her to clean a surface, and in the afternoon, it might be the quality of it might be different. But if we use automated process, like in this case, we use plasma. It's basically more like a CNC. You can program it. You can basically use the plasma stream to clean the surface. But after you clean it, how do you know it's cleaning is done properly? So we use another technique called FTIR, and this IR, basically IR techniques. IR can pick up the composition of the chemicals on the surface. So if you have different material, like you have oil that contaminate on the surface, the FTIR can pick up the signal, say, well, there's a peak that shows the certain chemical bond that only oil has. So this basically we use in this, you can see the surface tension. You probably know that from other work. And by the way, this is a work that in collaboration with Dr. Zhang of ISYE, we actually use data analytics to basically pre-process the data from the raw data from FTIR. We actually can enhance the measurement. We even can quantitatively analyze the contents of the contaminants. Like for instance, there's oil there, and how much oil is it? Is it a very small, tiny amount, or is it a big amount, and all that? So we can I wouldn't say purely quantitatively, but quasi-quantitatively. So at least we can show the amounts, rough amounts of those contaminants. So this actually can help the bond, okay, and surface analysis and surface treatment. So those are ongoing work, and this is another ongoing project that is sponsored by Delta. We're actually making some coupons and testing those coupons, and then we use machine learning to develop a material and process models for helping their repair processes. And this is another area of work, that quantitative NDE. Like I mentioned, we're actually combining a lot of different NDE techniques, like ultrasonic, guided wave, the thermographics, and then the like X-rays. We actually combine all this data. A lot of them actually is the complex images, and we use machine learning to actually quantify what is the defects or kissing bonds. So this is actually generates like here. So you have some testing, coupons, and then you have this NDE data, and through those images and data, we can get this machine learning model. So this is an ongoing project. A final project that I want to quickly talk about is the a couple of years ago when we visited Delta, they talk about using some new technology like augmented reality. So you probably can see that on the left is the traditional like training of technicians, right? So they take courses, and then they go to practice in the field, and then they got to train. But in the future, we think you can use like a AR, VR, the Google Glass type of goggles, and then you can actually get trained by that with a much higher efficiency and quality. And also this can also help guide the technician to do the real repair process. So it can reduce the cycle time, but also reduce the operation errors. This has been proved by many other applications. So what we're thinking is discussion with Delta and other industry partners. Like for instance, if somebody, a technician wanted to repair a structure of the aircraft, and then they probably wanted to know where to put the the screws, whatever, or remove them or put it in. So they need to know what's underlying structure, right? It's like the stop finder you can buy from Home Depot, but aircraft is different, so the stop finder doesn't work. So this actually is a similar idea. If a person has the Google Glass, and then they can display the structure CAD model, but also when you move your hand to a certain area, they can actually show you what is behind the structure. So this is actually the AR application for this. So this is an ongoing project. Okay, so those are the what's going on in GTMI in this area of research, and we have a lot of ongoing projects and some planned projects. I want to spend another maybe 3 minutes to talk about the next step. So since we have done a lot of work in this area, we got a lot of requests from industry, and also as part of the phase 2 of that NIST project, we should develop a consortium, industry-led consortium, to really develop technology in this area and deploy them. So how do we do it? We found out in National Science Foundation, there's a program called IUCRC, Industry University Cooperative Research Center, and that actually provides seed fund to formulate this consortium and for the basic operation. But then the research, dollars will come from the industry. So this actually is a pretty good model for us. So we actually just submitted in August. We submitted a proposal to NSF IUCRC. We were planning to form this center called the Composite and Hybrid Materials Interfacing, CHMI. The goal is to start this consortium by spring 2021, and we have 3 university partners. Georgia Tech is the lead. We're going to focus on the processing NDI and data analytics, and we're focusing on Aero, applications. University of Tennessee, Knoxville is another partner, and they are going to focus on the materials, but also focusing on infrastructure, energy, applications. And the third university is Oakland University in Detroit area, and they're focusing on testing and processing, but their focus is on the auto and ground vehicle applications. We have collected support or commitment from over 35 companies, and Georgia Tech is roughly about 10 now. And the membership, if we got this grant, the membership will work like this. All the companies committed, they'll join either as a tier 1 or tier 2. Tier 1 annual membership fee is $30K. Tier 2 is $15K. The tier 2 is primarily designed for small businesses. And then, so we collectively, we got all the memberships. We got an SF operation, fund, and then we will start to run this center. So the center, you can see it's we have primarily four areas for application, aero, auto, infrastructure, energy, and then protective gears, and then the vehicles. And then, like I said, the 3 universities involved, and then there are 35 companies currently involved. And so those are the 4 area of technologies. If you look at those yellow boxes, and so design, modeling, analysis, testing, NDI, material processing, automation, and then secure data and digital technologies. So those are the specific of those 4 areas I want to, just show you here. But if you need the detail, you can look at the slides later. I want to show you, this is for Georgia Tech side. These are the companies right now committed for this center. And so you can see in Georgia Tech, we have all those major, like Air Force, Life Cycle Management Center, and Autodesk is a software company, right? So they will help with computational modeling, and Boeing, and like the Solvay is a material company, Spirit is basically a supplier to Boeing. So you can see all this are major companies in the aero areas. But also we have potential members that we contacted, and they're interested in it, but because of COVID-19, so they're kind of have a delay for submitting the commitment. But many of them probably will join us later. So right now we have annually we got about $250,000 already, and NSF require at least minimum 150. So we already over that. So I'm pretty confident that we probably can run the center early next year. Anyway, so that's pretty much all I have, because I know we have only about 5-6 minutes left for question and answer, so I want to stop here. So this basically shows the acknowledgement. So from all the company and National Science Foundation, but also I have a lot of people I wanted to acknowledge that they are involved. They were involved or are still involved in the research and the roadmap development, and then some graduate student and GTMI facility and staff support and all that. Finally is my contact information. If you need like the roadmap or have other technical questions, please feel free to contact me by email or phone. Thank you very much, and I know we need to leave a few minutes for question and answer. Thank you very much.
Thank you very much, Dr. Zhang. We really appreciate you sharing what you're doing and what Georgia Tech is doing in the field of composite joining and repair. This is very exciting, and it's interesting to hear how many different industries can be impacted by this work and research, especially the transportation industry. So thank you again. We do have a question that was submitted by an audience member. What physical quantities currently do you measure with the printed sensor array? How do we decide the density of sensors to be printed?
Right now we're measuring 2 things. One is the pressure, one is curing, right? So the you can consider as this is we're measuring some electrical signals like a capacitance, and then that capacitance actually relate to the pressure, and then also we can measure the temperature using that sensor, the all electrode. The density, it really depends on the resolution you want, right? If you only want to average, let's say if a piece of like a 6 feet by 6 feet, if you want just a like in the middle area, you can print just a few lines over there. It will give you a average parameters of pressure or temperature in that area. But if you want a very detailed resolution, then you need to print a lot of this the electrodes. That of course that will complicate it, the data analysis and everything. But in the lab, we only I think our panel is like a 10 inch by 10 inch. We basically print 8 lines by 8 lines so that we can monitor that kind of resolution.
Great. Thank you, Dr. Zhang. So I actually have a question for you while we wait for other questions to come in. And you mentioned during your presentation that TRL and MRL are factors as you were putting together the roadmap in composite joining repair. I was wondering if you could take a moment to elaborate on what you mean by TRL and MRL and what the implications are. And this may be informative for some students joining today who haven't had the chance to in industry yet.
Sure. Yeah. Well, thank you. Yes. Those two parameters are heavily used in industry or defense field. And TRL means technology readiness level. They actually have 1 to 9. Okay, this is done by NASA many years ago. So basically, at that time when they developed this, they wanted to evaluate or assess a technology whether or not it's mature to put in the space, right? So they like 1 basically is very low. It's just like an idea. 2 is maybe idea plus a little bit theoretical analysis. 3 is have a limited maybe testing with analysis, but it's done in the lab. And 4 to 6 is more development that validate in the lab and also is ready to do mass testing and all that. 7 to 9 is pretty mature, and basically the industry can start to commercialize them or take them and then maybe do a little more manufacturing testing, and then they do the final production. So that's a TRL. MRL is very similar. It's done by DoD. So they want to make sure that the DoD systems and not only the technology, you can assess it using TRL, but they also want to make sure that we have the materials and the facilities and manufacturing, companies and all that are ready to mass produce those equipment or structures or systems. And so the MRL is much more detailed, but also is more focusing on manufacturing instead of technology. Okay, so that is if you are interested in that area, you can actually Google search. There are a lot of information that about the MRL. So yes, those two are actually pretty important parameters for researchers, but also for the technology development companies. They need to make sure that those things are assessed before they go into the new system or new product production.
Thank you very much. So we are at the end of the hour, and Dr. Zhang has offered to share this presentation. If there's anyone who would like a copy, he's provided, or if you have further questions that come to mind, he's provided his contact information on this concluding slide that you see here before you. And we are also recording today's presentation. This will be posted to the Georgia Tech Manufacturing Institute, or GTMI, website shortly, so feel free to visit that website in a few days, and we should have this presentation available, and you can share it with colleagues or fellow students as well. And please join us next Monday, October 19th, also at noon for our next Lunch and Learn series. Our speaker will be Eric Bosenhart from Integrated Project Services, and Eric will present cell therapy facility design. Thank you again, Dr. Zhang, and thank you to our audience members for joining us today. Have a wonderful afternoon.
Thank you very much. Yeah, thank you. Yeah. Bye.